and we'll post this later. So the idea and the reason why I want to go over a bunch of problems is that honestly, energy can be used to solve nearly anything. Um, it turns out energy is super useful, but that also means that a lot of us are lost. You're not exactly sure how to even begin these problems because you can basically do them any way you want with energy. So you need to have some kind of algorithm or some kind of recipe or some kind of strategy that just applies to every energy problem. And it turns out it's really simple. And hopefully I can show you that. There's a few little things. This first problem is about what your quiz is about. So we'll talk about that. But then as we go, we're going to see a bunch of different types of problems, and we're going to solve them all using the same strategy, which is really helpful. Okay, so this says that a luge is a person on a sled, slides down a hill. They emerge onto a horizontal track, and their total mass is 69 kilograms, and their initial speed is 37 meters per second. They are slowed down by friction with the surface at a constant rate of 4.5 meters per second. So the first thing it needs, and I gave myself room to do these on multiple sleds. I'm going to probably do these right here. The first thing they ask is, what magnitude of F is stopping us? So we have, and I find it helpful to draw. I generally don't ask you to draw too much for energy problems, but we have, I'm going to use a block for it. It's initially doing 37 meters per second, and it's being slowed by friction. That friction force is MA, and they gave us A was 4.5, and the mass was 69. So if you multiply 69 kilograms times 4.5 meters per second squared, you're going to get 310.5 newtons. That we should all know how to do already. It is technically negative, but they said the magnitude. But that force is a force of friction, and it's causing it to stop so that V final is 0. Okay, I hope everyone has that. And if you have a question, just hop on in and ask me. So now we need to know what distance does it travel before it stops, okay? So we need the work energy theorem. And the work energy theorem says that the work is the change of kinetic energy. We know the work is force dotted with distance. Force is that way. Our distance is that way, okay? So this is going to be negative. And that's equal to the change in kinetic energy, which is mv final, always final, minus mv initial, okay? But we know that v final is 0. So our signs are great. Our signs totally work. But we need to know how far it stops. So we can divide by negative f on both sides. We get m v naught squared over 2f. We found f was 310. So this becomes 69 times 37 squared over 2 times 310.5 newtons. And if we do that, we could check that with our calculator. I'm not going to right now. I know it's 152.1 meters. But that's all you do with the work energy theorem. It tells you that the force dotted with the distance is the change in kinetic energy. And at that point, it's really a matter of making sure that you get your signs right for your vectors, and making sure that you know what V final or V initial is if it's 0. So in this particular problem, you might notice that it doesn't quite say, I mean, it says like right here, slows them to a stop, but that little tiny word right there tells you so much that you need to know. So you really need to read these carefully and understand what's happening. And then it kind of guides you through this problem and make sure that you understand how force and distance are related to changing kinetic energy. Also remember that if the force is in the opposite direction of the displacement, it's going to slow it down. and therefore it's negative when the force and the displacement are in opposite directions. The last thing I would say is always remember that delta is final minus initial. Okay. All right. So what is the work done? Well, this is kind of easy. Work, we just said with changing kinetic energy. So that's mv final squared over 2 minus mv initial squared over 2. This is 0. This is negative 69 times 37 squared. So that's just the definition of work. And that will give you this big 47,000 number. They then ask, okay, well, what if we change it, we double the acceleration? Well, that means that we're doubling the force. We're doubling the force from m times 4.5 to m times 9, right? Because 9 is double of 4.5. If this is double, right, then our distance is half. And if this is double, then our work is double. That should be easy to see. And then, I'm sorry, our work is not doubled. Why isn't our work doubled? Oh, because it slows in half the time, because I'm dumb. I better do those ones. Okay, so if we got that f dot d with a negative was negative mv naught squared over 2, and we got d was mv naught squared over 2, and if f was now 2 times f prime was now that, then this would be, our new d would be mv naught squared over 4f. So it would, this d prime would be half of d. And then the work should be the same, because the work is just mv naught squared over 2 with a negative sign. So yeah, it's being weird, sorry. But yeah, this problem is really just using this equation f dot d is equal to mv final squared over 2 minus mv initial squared over 2. That is called the work energy theorem. And if you know how to do it, this problem is actually pretty easy. Okay, let's move on. This problem I actually really like. This problem is one of those problems that you might think is really easy and not realize how many different concepts you have to understand to get this correct. So we have a helicopter lifting an 86-kilogram astronaut 15 meters vertically with acceleration. Okay, so there is acceleration here. There is a force due to the helicopter doing work on this astronaut. But there's also work being done by gravity. So if the astronaut were like bouncing on a trampoline and went up, the force of gravity would be down and the astronaut would go up. The force due to the helicopter is up while the astronaut goes up. So the work done by gravity is the force of gravity times d is negative. They are 180 degrees off. F dot d is f d cos theta, where theta is the angle between these guys. That angle is 180 degrees. That means this is negative. Okay, that means this is negative mgd. The work done by the helicopter is fh times d, however far it lifted. Positive because they're in the same direction. So now we need to figure out what these are. So if the acceleration, the net acceleration, is equal to the acceleration due to gravity, negative because it's down, and the acceleration due to the helicopter, up, this has to equal g divided by 12. So AH is g plus g to the 12th, or 13g over 12. Add 12 over 12. So we know what the acceleration of the helicopter is. And now what we need is we need to know the work done by the force of the helicopter. The force of the helicopter is mass times the acceleration of the helicopter, or 86 times 13 over 12 times g. The work done by this is FHD, and we said that they're positive because they're in the same direction, which is whatever this ends up being, and I'll run it in a minute, times the 15 meters. If I check those answers, I'm going to use 9.8. I'm not sure what Wiley used for this particular problem, but I'm going to use 9.8 for G. I get 913, that this whole thing is 913 newtons. So 913 newtons times 15 gives me 13695.5. So they did use 9.8 for G. Okay, so make sure you understand how to figure that out. It's a little tricky. You have to figure out the acceleration of the helicopter using the acceleration of gravity and the acceleration that you're given. That's about the only hard part. The rest of it's just the definition of work, that work is force dotted with D. The work due to the gravitational force is, again, negative mg. Negative because gravity is down, the displacement's up. So this is negative mgd, if this is the force of gravity. And this is negative 86 times 9.8 times 15, which if I do that, I get 86 times 9.8 times 15, 12,642 with a negative sign. Work is in joules. So just before she reaches the helicopter, we need her kinetic energy and her speed. And we should actually find those in reverse. So we're going to assume that she was lifted from rest with an acceleration of g divided by 12. Okay, we could do this another way, but I'm going to do this way first. And that we went a distance of 15 meters and we started from rest. We're going to assume this was a constant force or a constant acceleration, and therefore we can use our constant acceleration equations. With this being 0 and no time, we're going to use v final squared minus v initial squared is 2a y final minus y initial. This is our y final, our y initial is 0. This is 0, this is 0. So we get that v final is 2a y final. Take the square root. A is 15. I'm sorry, a is g over 12. So this is 2 times 9.8 divided by 12. I can't write. Times 15, which is 9.8 divided by 6 times 15. Take the square root of this answer. I get 4.95 meters per second. That's the speed. If I take this as a magnitude, that's the speed. If I want to know the change in kinetic energy, the kinetic energy at the top anyway is mv final squared over 2. I don't know what her mass was, 86. 86 divided by 2 times 4.95 squared. 86 divided by 2 is 43. 43 times 4.95 times 4.95 is 1053.6 joules. All right, so now let's go back and look. This was her kinetic energy at the top, and 4.95 was her speed at the top. I went backwards to solve it, but you could have solved it either way. And I wanted to show you that. You know that the work done on her the total work done is equal to the work done by gravity plus the work done by the helicopter. And that work is equal to, we wanted the change in kinetic energy. So that work has to be equal to the change in kinetic energy. We said that the work done by gravity was negative 12,642. And the work done by the helicopter was 13,695.5 is equal to, the change in kinetic energy is mv final squared over 2 minus mv initial squared over 2 and kill that. So what I get here is I get 13695.5 minus 12642. That's 1053.5 joules is her kinetic energy final. And if I then wanted to find her final velocity squared is 2 over m times 1053.5. Take the square root. I get 2 divided by 86 times 1053.5. Take the square root of that answer, and I get 4.95. Not surprising. So you could have done this either way. And probably the better way would be to do it with the change of work is your kinetic energy. If that was all you were asked, was to find the final kinetic energy. Change of work is the change in kinetic energy. And she had no kinetic energy to begin with because her initial velocity was 0. But you certainly could have done it with constant acceleration too, and we would have gotten the same answer. Sometimes it's worth doing it both ways just to check and make sure you haven't forgotten something important. But are there any questions on these first 2 problems? They're all work energy. And in general, almost everything else we're going to do a different way. So you really have to have these concepts down for those. Okay, this is actually a super easy problem, but let's make sure that you understand it. So the power is the change of work over the change of time. Technically, this is the average power. And whenever you have these problems, you need to usually figure out what is the work. And that's where you're like, okay, well, the work is F dot D. And if I have the change of work, that's F dot D final minus F dot D initial. This is the work. So we know that we have 140 passengers that average 610 newtons. So we have 140 times 610 is our weight. And weight is the force of gravity. Okay, so we know this is our force. Our force is 140 times 610 newtons. Okay, it brings it from a height of 0 to a height of 143 meters. So how much work is done? Well, this is our D final, this is our D initial, and our work is mg, or 140 times 610 newtons. So this goes away, and we get that the work is 140 times 610 times 143 joules. I should really call this delta W. So 140 times 610 times 143 is a huge number. It's 12,212,200 joules. Now, we want the power though, and power is the change of work over the change in time. It's how much work changed in a given amount of time. We're told that it did this in 45.6 seconds. So if we take this work and divide it by 45.6 seconds, so this is delta W over delta T, divide that by 45.6, and I get 267,811 watts. Watts are joules per second. They're the energy used per second to do work. That's what power is. The power in your car is the force needed to be applied to make your car move a certain distance. And that's usually listed in horsepower, which is a little different than watts. There's a conversion factor. There's a lot of other, I don't know if I talked about this, but energy and power have been around a long time. And so there's a lot of weird units for power or for energy. You know a few of them. Horsepower, you probably don't really have any idea how much like 10 horsepower is. If you're a car enthusiast or a motorcycle enthusiast, you might know what 100 horsepower means versus 200 horsepower. And there's different types of horsepower. It gets ridiculous. For us, I'm generally not going to ask you to convert from horsepower to watts or any of the other weird units for power. It'll usually just be watts. Just remember that the definition is found in power. It's work over time or joules over seconds. That is the watt. And Watt was a guy who was a scientist that did a lot of work with steam and thermodynamics. All right, so this is kind of the last one before we start doing the fun problems. All these problems I took out of chapter 7. This is probably the one problem that would throw everybody if we did it on an exam. So we have a block that slides down a frictionless surface, frictionless incline, 1.3 meters along the diagonal. So let me draw this really fast. This incline, we're not given the angle, but we're told that it starts, say, here, and it ends up here, and that this distance is 1.3 meters. This distance, we're told, is 0.56 meters high. And a worker is pushing against it as it slides down so that it has no acceleration. V is constant, okay? So we need to figure out, and you might think, oh, well, the acceleration is 0, V didn't change, so the kinetic energy didn't change. So this thing should be 0. And you know what? You're right. There's no net work done on this, but there's definitely work being done by gravity, and there's work being done by the worker. So we need to figure out what some of those are. So the first thing that we need to do is we need to go back to what we already know, not about Newton's equations, but about, well, from Newton's equations. We can find this angle if we want, because this is 100 or 1.3, and this is 0.56, 0.56. Remember SOHCAHTOA? SOHCAHTOA says sine of theta is opposite over hypotenuse, or y over h, or y over r if you want, which is 0.56 over 1.3. Take the arc sine and we get this angle if we need it. That's step 1. Sorry, arc sine. I find this angle to be, and I think I'm in radians, so I'm going to change. Arc sine in degrees of 0.56 divided by 1.3 is 25.5164. 5.5164 degrees. All right. But we were asked to find the magnitude of the worker's force. So the worker is pushing that way so that this thing comes down. And we know that when we do this, we have, for this block, it has the weight mg sine theta, and it has the force due to the worker. And I don't care about any of this other stuff. This is frictionless. So doing Newton's equations again, ma is, this is why we always take it to be, I'm going to go this way. My acceleration in the x will be positive up in the direction of the worker, minus mg sine theta. So the magnitude of the worker's force is what? Well, we know that this is constant velocity. Constant velocity is 0, F minus mg sine theta. You probably could have guessed this without all this drawing, but this is the force that the worker has to apply in order for the thing to slide with no acceleration down the plane. Okay, so here's where things become super easy. And once we know that, everything else in this problem is easy. How much work is done on the block by the worker's force? We just said that the force was mg sine theta. And if we look this way, the force is up and D is down. So F dot D, the angle between F and D is 180 degrees. This is negative. So the work has to be negative negative mg sine theta times D on the incline, which is negative whatever they gave us, 39, 9.8, sine of 25.52, I'm just going to call it, I guess I will round, times d along the incline. So the distance that this thing traveled while the force was being applied. When we do all that, I get 39 times 9.8 times sine of 25.2 times 1.3, and I get 211. I rounded something weird. They get negative 214. Now, here's where the rest of this gets easy. The gravitational force done by the block, you could say, well, okay, the change of gravity goes down, and it's mg cos theta, right? Well, let me not do it quite that way, because I really don't want to do that way. The force of gravity is mg. It is flat down. The force of gravity is down. D is also straight down, but D is 0.56. So the work done by gravity is Fg dot D, but they're in the same direction. So this is mg times, call it y if you want. That is 39, 9.8 times 0.56. And it brings up a really good point, but let me make sure that I get the right answer before I move on. What do I have? Oh, 0.56. Yeah, I get 214 down. Now, a couple things that are super important here. This is the part that you really need to pay attention to. The force that the worker was applying, he was applying it up the incline, and the displacement was down the incline. So the worker was doing negative work because his force was actually acting opposite to the direction that the block traveled. That is negative work. The work was done along D, and D in this case was the incline. But gravity did work straight down in the Y direction. Even though the block was sliding, we only care about what the change in height was, because that's the change in potential energy of gravity, and that is mgy. We have to take y to be 0 at the top and y to be 0.56 at the bottom, take it positive down, but we know that gravity and the displacement downward are in the same direction, so gravity is doing positive work. If you're forgetting what those mean, positive work means it speeds up. Negative work means it slows down. The worker is actually slowing the block down while gravity is speeding it up, and they're exactly even so that the block moves at constant velocity. Okay. Now, what about the normal force? The normal force is actually acting perpendicular to the displacement down the incline. Well, a force can't do work if it's perpendicular. Force times distance times cosine, but cosine between the force and the distance, if it's perpendicular, is 90 degrees. That's 0. So the normal force off this incline can't do any work. And the net force is 0 because constant speed. And that's all you need for this.
Professor?
Yes.
I have a quick question about the quiz.
Mm-hmm.
I'm doing it right now, but for number 2, so since it's a frictionless horizontal surface, so the theta is 0, correct?
Yes.
Okay, thank you.
Cool. All right. So that was the end of the chapter 7 kind of force and work and energy. Now I'm going to show you where things get easy and fun, if you like this stuff. Oh wait, no, not quite yet. Yeah, sorry. Yes. Okay. Before we do that, though, we're going to talk about something. This is technically a spring problem. You can think of this as a spring problem, but it's really a restoring force problem. But anyway, we're told that we have a mass that's 2.2 kilograms, and that it's moving in the x direction. But it's subject to a force in the x direction, which is negative, a force that is 8 times x newtons. Okay. And then initially it's at a position, x is equal to 2.5 meters, and it's moving at 9 meters per second at this point. And that we want to know, first thing we want to know is when it gets to, with this force doing work on it, when it gets to x is equal to 4.5 meters, we want to know how fast is it going. Now, in a weird way, I already know this, but if we assume that the force times dx is going to give us the work done, that means that we get k x dx, where k is 8. And what this ends up being is a spring problem. For these problems, if we pretend this is a spring problem, we just have to do one simple thing. When the block is at x is equal to 2.5 and traveling at 9 meters per second, and then when the block is at 4.5 meters, we don't know b. So I'm going to call this xb, bb, ba, xa. This is my point A, this is my point B. The energy at A, because this is a restoring spring force, mva squared over 2 plus k xa squared over 2, where k is 8. The force due to a spring is minus kx, which is exactly what this is, where k is 8. This is mvb squared over 2 plus kxb squared over 2. This is the first step of these problems. Well, the second step. The first step is making sure you pick 2 points that you want to know the change in energy. Then you just write down the kinetic energy, the spring energy, the gravity energy, the whatever have you. So we've done that step. We've written mva squared over 2 plus kxa squared over 2. This is energy A by conservation of energy. If there's only spring forces and gravity, then this is always true. And then what we do is we were told that m was 2.2 and k was 8. We had to look at that, but xa and va were 2.5 and 9. And xb was 4.5. Okay, so now let's solve this for bb. We get mvb squared over 2 is equal to mva squared over 2 plus kxa squared over 2 minus kxb squared over 2. If I multiply both sides by 2 over m, and then I take the square root, I get that VB is 2 over m times m to the half gives me VA squared, plus 2 over m times this gives me k over m times xa squared minus xb squared. And so I could put in VA was 9, so 9 squared plus k was 8, because I know the force is minus kx, and we were told that was minus 8x. So 8 over 2.2 times 2.5 squared minus 4.5 squared. Sorry, put that in the parentheses. If I get that, I get 81, that's 9 squared, plus 8 divided by 2.2 times 2.5 times 2.5 minus 4.5 times 4.5. And I get 30, take the square root of this answer, and I get 5.49. So this is 5.49 meters per second. Why did it slow down? It was doing 9 and it slowed down to 5.49. Slowed down because the force was acting opposite the displacement. That means that the work was negative. Negative work implies a negative change of kinetic energy. Kinetic energy is dependent on V, so it slowed down. Now, if we want to do at what positive value of x will the velocity be 2.6, we can do this all over again, but you plug in 2.6 here instead of 4.5, and that's all you do. The algorithm on these problems is write the energy in the types of energy it has, and then set them equal to each other. And that's all you have to do. All this other stuff that we've done, it's basically the backbone that you never see. It's like the wood frame inside your house. You don't need it. You don't need to know about it. You can just write down the energy, the types of energy it has at each position, set them equal. And as long as there's no friction, they're all equal. And we'll see that in, I think, the next problem. Nope. We'll see it in the problem after this problem. Okay. This problem is a little weird, and it may throw you a little bit. Basically, we need to decide whenever we have a spring, where the zero, the equilibrium of the spring is. They've chosen in this that these 3 blocks, their zero is being measured here. The first block weighs 110 newtons. That means M times G is 110. And when they attach it, it causes the spring to stretch 40 millimeters. Now, 40 millimeters is how many meters? 0.04 meters. The 240 Newton one causes it to stretch 60 meters. The third one, or 60 millimeters, I mean, the third weight unknown causes it to stretch 30 millimeters. Okay, so just be clear that that's what's happening. What this is doing is that we're finding when kx squared over 2 plus mgh is equal to 0. We'll get there in a minute, though. Okay, so in order for this to be 0, though, we have to choose this 0 to be our x is equal to 0 and our y is equal to 0. And y has to go up positive. If it doesn't, we're going to get a weird sign issue here. Okay, so yeah, I guess we don't have to, but we should. So which mark on the scale will the pointer indicate when no package is hung from the spring? Well, it'll be at, why would it be at 23? Oh, because I'm assuming bad things. I'm sorry, you guys. I'm assuming that we know where x is equal to 0, and we don't. What we know is that do I want to say that? Oh yeah, I'm stupid. Sorry, guys. It's been a long day already. Before I do any of this, I should stop. So for this one, let's just write down the energy for this guy. And let's write down the energy for this guy. We know that mg is equal to 110 newtons. So this mass, which I'll call mass 1 is equal to 110 divided by g. E1 has to be mgh plus kx, put 1s here, squared over 2. Now, we're going to assume that these are 0. And E2 is equal to mgh2 plus kx squared over 2. When we do that, we can set those equal to each other to find K. And that shouldn't be too hard, assuming that we're calling that 0. Let me check one really fast thing now and see what they did, because I just totally messed myself up on this problem. I want to make sure I don't waste a bunch more time on this one stupid problem. I believe this problem is, where my stupid book went? Right in front of the face. This problem is problem 67 and 7. Come on. Okay. So we have, oh, right. So they do basically find K in this problem to get it for 6.5. So we can find K here, but what I've kind of messed up along here is they're not assuming MGH. So once they do that, then they can use okay. I know what I did wrong. So for the first one, we're going to assume that mg is 110 newtons. And this force, this block, is initially at some x naught, and then it's at x final, where x final is equal to 40 millimeters, which is 0.04 meters. We don't know what the x initial is. We're assuming it's 0, but we're actually going to figure out, well, it is 0 though. So what did they do here? Oh no, we just don't know what it is. Okay, got it. And then the spring force here. So the spring force down, Fx, has to equal this. Okay, so F of x has to equal, well, actually, I shouldn't say that. F is Kx final minus x initial, and that has to be equal to mg x final minus x initial. And man, I am making a mess of this whole thing. Nope, just mg. Yep, I'm completely lost my way on this. Sorry, guys. So this is equal. And what they're saying is the change of the spring force has to be equal to the force of gravity by energy considerations, by force considerations. It's hanging and A is equal to 0. There is a force due to the spring. There is a force due to gravity. And there is a force due to the spring. because they're equal and opposite, they're equal to each other, but the acceleration is 0. This is the change of the spring force, and that's equal to mg. K, if we assume that this is 0, then mg over x final, which is 110 over 40, gives us K as 6.5, I think, or whatever it was, 2.5, 2.75, 2.75 newtons per meter. So once we have that, I guess I'm not assuming X is, okay. Forget everything I just said. I hate this problem already. I know what I did. They said that mg minus kx for 1 was equal to m2g minus kx2 for the other one. Because k is the same, this gives you m1g minus m2g is equal to k x1 minus x2, where x1 is our 40 millimeters, x2 is our 60. So this is 0.04, this is 0.06. This is 110, this is 240, minus 240 is equal to k. K is therefore equal to, this is minus 130 is equal to minus 0.02, which is equal to, and I don't know why they got such a small number for k. Oh, because they went per millimeter. So this is equal to 130 over 0.02. 130 divided by 0.02 is 6,500. If I want that, newtons per meter. If I want it in millimeters, that's 6.5 because there's 1,000 millimeters per meter, newtons per millimeter. Once I have that, as you can see in the solution here, these two equations are true. And once I have k, I can find x final for either one of these. That was what I was doing here, trying to find x final. So 110, and I guess this should be negative, right? Yep. This should be negative, so yeah, it doesn't matter. So 110 divided by k is equal to 0, they're calling it millimeters, 40 millimeters minus x naught, or 110 divided by 6.5 newtons per millimeter. 40 minus this is equal to x naught. That should give me 23. 40 minus 110 divided by 6.5 is 23 millimeters, 23.07 millimeters. Okay, once I have that, I know what x naught is. So x naught is where the equilibrium of the spring is actually from 0 is 23. Okay, so here's what I do want to show you that will make sense. So if our equilibrium point of our spring is 23.07 millimeters, and we know that k is 6.5 newtons per millimeter, and we want to know what the weight is. So we want to know what mg is. We know that mg has to equal k of x minus x naught for this guy. Okay, x is 30. X naught is 23.07, and k is 6.5. Those are all in millimeters to give us this. There's a weird issue here, which I'll talk about in a second. So 6.5 times 30 minus 23.07 gives me 45 newtons, but it should be negative because it drops down. That's what they got, thankfully. I didn't totally mess that up. But the point is, this is one of those weird problems where you have to be able to say that the force of gravity and the force of the spring are equal and opposite. And then from there, you have to know that this is Kx and this is mg. And from there, you have to know that there's always an equilibrium point on springs. There's always a 0 point. And how they made this problem hard, which when I picked it this morning, I didn't realize I was going to mess it up this bad. There's always an equilibrium point, and usually you call that 0. Here they didn't. Here the equilibrium point, they just measured 0 from some random spot, which is a little odd. Anyway, moving on. I don't want to deal with that problem anymore. I want to get to stuff that's actually useful. This problem is something called a roller coaster problem. And no problem illustrates what I'm trying to get through to you guys, more than these. It looks like a roller coaster, right? Well, we say that at A and at B and at C, it's got a certain energy. You can see that this thing's got a mass of 929 kilograms at H, which is technically A. Where it's at here in A are exactly the same. So we're just going to say that it's at A and forget about this whole stuff. At A, it has a velocity of 19.8 meters per second. It's at a height of 47.4 meters. Now, I'm going to find the energy at A, the energy at B, and the energy at C. All I have to do, I don't have to think. Don't think. Write down mv squared over 2. It has kinetic energy at every single point. Worry about which ones are 0 later. But for now, write down mva squared over 2, mvb squared over 2, mvc. Write down mgha, mghb, mghc. And if it had a spring, we could write down springs. There's no springs in this problem. If we had friction to worry about, we'd worry about that. We're going to do some with friction later, but we don't have to worry about that now. This is all we do. You don't think, you just write. Then all you need is you need VA and HA, and VB and HB, and VC and HC. So the question is, where do we want to put 0? We can choose H to be 0 anywhere we want. Well, they chose it for us because they already said that A was at positive 47. That has to mean that C is 0. If C is 0, get rid of that. B is H to the half, which is HA to the half. HA is 47.4 meters. We know at VA, this was 19.8. And I'm not going to write the meter per second. We don't know VB, we don't know VC. But what we do know is that EA is equal to EB is equal to EC. Now, before we move forward, we now need to know, what does the question want to know? The question wants to know, how much work does gravity do on the car from point A, from the initial point to point A, then to point B, then to point C. Gravity, the work done by gravity, is the change in potential energy of gravity with a negative sign. That means it's mgh final minus mgh initial, but with a negative. So we need to find mgh initial minus mgh final. And that's the work done by gravity. So we know this thing weighs 929. This is technically mg h initial minus h final. So this is 929 times 9.8. And then for each one, we'll just plug in the values. So initial minus final, the change is 0. Of course, that's 0. From A to B, it's half of 47.4. So this is 47.4 minus 47.4 to the half. If I plug those in, I get 929 times 9.8 times 47.4 times 0.5. I get 215,769. Positive or negative? Well, it's positive because it's going down. It's dropping. It would be negative had it gone up. And then from the first point to C, it's actually dropping all the way to H, which is double B. Because this would be H, it would be 47.4 minus 0. Okay. So it's just double what we got for this answer. Now, it says if the gravitational potential energy is taken to be 0, what is the value at B and at A? Well, the gravitational potential energy is mgh, mgh, mgh. It's 0 at C. At B, it's 47.4 divided by 2 times mg, which is 215,769. And at A, it's mg times 47.4, which ends up being this 43. The idea of this problem is just to make sure that you understand how the potential energy of gravity changes with height. Okay. Now, then, moving on. Why it's called a roller coaster is you can just write down the energy, but let's do it here for this truck. Now we have a truck, and in this truck, the truck's runaway truck, it's moving down at 158 kilometers per hour before they steer it up an inclined ramp. The mass is 1.3, blah, blah, blah. What is the minimum length for the truck to stop? Now, we're going to assume that this truck's a particle. We don't need to justify it. We could, because essentially its center of mass is the only thing that matters. That's where gravity is being applied, is at its center of mass. So we assume it's a particle at the center of mass of the truck. That's the justification. I don't know why they're asking you to do that here. We do that later. But the length to stop. So what stops this truck? What's stopping this truck is the force of gravity as it goes up the ramp, right? As it's heading up the ramp this way with B, it has a force on it of mg sine theta, okay? That's the weight going down. That's the only force acting on. Ma is mg sine theta. So what we need to figure out is however much kinetic energy it has here to how much potential energy of gravity it ends up with here. I shouldn't actually do that mg sign. What I should say is that this problem can look the same as this. He has got a kinetic energy of mv squared over 2. And they told us that the kinetic energy was 158 kilometers per hour. We'll talk about changing that as well. We'll do it now. 1 kilometer is 1,000 meters. 1 hour is 86,400 seconds. No, it's not. 3,600 seconds. 3,600 seconds in 1 hour. Those die, and we get 1,000 divided by 3,600 times 158. He was doing 43.89 meters per second when he hits this ramp. So at the bottom of the ramp, at A, he has all kinetic energy. And so we're going to set H equal to 0 at A. At the top, he has kinetic energy equal to 0. We're going to call this B. H is unknown. All you have to do is energy at A and energy at B. Energy at A is mVA squared over 2 plus mgHA, mVB squared over 2 plus mgHB. That's it. That's all you have to write. These two things are equal. HA is 0. VA is 43.89 meters per second. VB is 0. HB, I don't know. Since EA is equal to EB by conservation of energy, and we're assuming there's no friction, we write MVA squared over 2, this is 0, is equal to, this is 0 since it stops, MGHB, these cancel. What were we asked? L. So L has to be equal to, we're going to have to find H, and then we're going to have to use sign. H will be equal to VA squared divided by 2G. And let's move to the next slide. So VA squared is 4389. 3.89 times 43.89 divided by 2 times 9.8 is 98.28. So HB is 98.28 meters, but we need L. And if HB is that and this angle is 12, then we know that HB is equal to the hypotenuse L sine theta, or L is sine HB divided by sine theta, which means 98.28 divided by sine of 12 is 472.7 meters in length. 472.7, I guess. There's some rounding there, but that's fine. Okay. Yeah. So what we did, remember, just to make this short and sweet, is we found at the bottom of the ramp and at the top of the ramp, we found the energy. Now, how did we find the energy? All we had to do was list the kinetic energy plus the potential energy of gravity, because that's all it has here. The kinetic energy is always mv squared over 2. The potential energy is always, of gravity, is always mgh. So it came down to finding h. For h, we choose our 0. We chose that this was 0. So at A, mgha was 0. And at B, we knew it came to a stop. And so at that point, we could set EA equal to EB, which meant that the kinetic energy at A was equal to the potential energy of gravity at B, or MVA squared over 2 had to be equal to MGHB, but they wanted length because it's Wiley, and Wiley always wants a little bit something weird. So we used our HB once we found it from that to get our length. The next thing that they ask us is, if you decrease the mass of the truck, would L increase? So we know that L is dependent on H and sine theta, but it depends on H. So what they're asking is, if the truck's mass decreased, if it weighed less, would we have to increase L? Does the mass actually figure into this anywhere? Look at our final equation. Mass, mass cancels. So HB doesn't depend on mass. It just depends on the initial velocity and gravity and 2. If the speed decreased, would we have to increase L or decrease L? Well, L would decrease. That's because this right here, this equation right here, if V decreases, H decreases. If H decreases, L decreases. Okay, that should make sense though. If it has less kinetic energy, it doesn't need as far of a ramp to slow down to 0. Okay, but really what I want you to get in your head is you just choose 2 points, find the energy by writing mv squared over 2 plus mgh, and then figure out your variables, set them equal to each other, and you're done. Not too bad. We have a couple more fun ones. This is actually the springs that I wanted to talk about. And hopefully they don't do this one, something weird on this one. So this spring was initially at some height. We don't know what height it was at. And it got pushed down by this weight, okay? It's compressed 11 centimeters. So it's been compressed delta X by 11 centimeters from its wrestling. What is the spring constant if that's true? We know that the stone weighs 8.3 kilograms. Again, mg is going to point down. Force of the spring is going to point up. And a is 0. So we have that kx has to equal mg, and k is mg over x, 8.3 divided by 0.11, 9.8. So our spring constant is 739.45. Once we know that, okay, we're going to push it down a further 30 centimeters. So if for part B, our change of x is now going to be 0.41 meters, and release it. What is the potential energy just before release? So let's think about this. We have this spring that we compressed from 0 down to negative 0.41 meters. And what we want to know is right here, what is the energy before we let it go? There is no V here. So our energy at A is mv squared over 2 plus kx squared over 2 because it's a spring, and x is measured from the 0 point of the spring, plus mgh, blah, 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 blah. But what they want to know is that what is the elastic potential energy in the spring? So that would be kxa squared over 2, or 739.45 divided by half times negative 0.41 squared. Doesn't matter if you put negative or positive because it's squaring it, but 0.45 divided by 2 times 0.41 times 0.41. I get 62.15 newtons. I'm sorry, joules. 62.15 joules is what the energy that's stored in the spring. That's the energy that once you let it go, is going to be turned into kinetic energy and potential energy of gravity as it goes up. What is the change in gravitational potential energy when the stone moves from the release point to maximum height? So now we're assuming that this thing gets launched, shoots up, it leaves the spring and comes up to maximum height. So initially, if we say this is 0, we can figure out that at maximum height, we'll just call it mgh. And we're going to measure this as our 0 point for our y. That'll make sense more in a minute. I'm trying to figure out, oh yeah, what is the change in gravitational? Well, here's the thing. At B, if we write this down, so let's look at this really fast. EA, EB. At EA, it only has kx squared over 2. We're assuming that when it's here, it's 0 for h. Call this y, I don't care. But h is 0 here, and h is big H here. X is 0 here. V is 0 here at maximum height. Therefore, and I don't know why I did that. I meant that one. At EA, it starts off with no velocity and no height. So no gravitational potential energy, no kinetic energy. All of its energy is spring energy. At B, it shoots all the way up. It's left the spring, so no spring energy. It reaches the top of its height. It has no velocity at that point, so it has no kinetic energy. And all it has is mgh. But EA is equal to EB, and we already found this. We found this just a minute ago. So mgh, the potential energy of gravity at maximum height, is the same as the elastic potential energy stored in the spring. They are the exact same value. That's the only energy that we put in the system. And then what is the maximum height that it reaches? Well, if this is true, that mgh is equal to kxa squared over 2, h is equal to K over 2 mg xa squared. And you can find that really easily. It's 76.4. So not too hard. But yeah, this is just to reiterate one more time. The algorithm is pick an A, pick a B, pick maybe a C. EA is equal to EB is equal to EC, as long as there's no friction. If there's friction, we have to do something else. But you write EA is MBA squared over 2 plus KXA squared over 2 plus MGHA, EB, etc. MBB squared over 2 plus KXB squared over 2 plus MGHB. Now, X and H might be exactly the same. You might set your H to be 0 at the same point that your spring, let's say we have a spring here, that we say that the rest length of the spring is 0 and the height are both 0 at B. We can do that. They might be different. It doesn't matter. But once you do, the next step is writing down VA, HA, XA, and getting rid of any terms that you don't need, that you know are 0. Now, that's the hard part. But I recommend that instead of being, to be a little bit, do a little bit of overkill. Write down every type of energy, even if there's not springs. Just get in the habit of writing MBA squared over 2 plus KXA squared over 2 plus MGHA, and then cross them off, everything that it doesn't have. I totally recommend you do that, because then you take your brain out of it and you just kind of make it a standard form every time for these problems. Anyway, let's move on to a slightly more fun problem. This is exactly the truck problem again, except we're going in reverse of that truck problem. So we have a skier. He's going down a ramp. We're assuming at the end of the ramp, he's going to launch at some angle. Okay. As he leaves, they give us that this angle is going to be 16 degrees. Degrees. That he's going to launch from. So we need to find V when he launches and get the maximum height. Just to remember that if V final squared minus V initial squared is equal to minus 2G Y final minus Y initial. If we have this is 0 and this is H is, and at max height this is 0, then what we get is H is equal to V naught Y squared over 2G, but we're going to assume, never mind, yeah. So this is V times sine of the angle over 2G squared. All right, that was just projectile motion. If you didn't remember how to do that, make sure you go back and review how to find the maximum height of projectile motion. But we need to find V, we need to find V naught. And so all we have to look at here is at A, he has, he starts from rest. So the energy at A is, again, MVA squared over 2 plus MGHA. I'm not going to write springs. He starts from rest, so the energy is MGHA, and HA is 22 meters. Told us that right there. His M is 51 kilograms. When he gets to the bottom, right? When he gets to here, what is his energy at B? Well, his energy at B, all you write is MVB squared over 2 plus MGHB. We're going to assume that this is 0, because that's already where they measured H from anyway. That goes away. We're going to assume that VB is V naught. So we get that EB is MV naught squared over 2, and EA is MGHA. Setting these two things equal to each other and solving for V naught, we get MV naught squared over 2 is equal to MGHA. That goes away. V naught is equal to 2GHA square root, which is square root of 2 times 9.8 times 22. I get 20.77, let's call it, meters per second. Okay, all I did was I found the energy here, got my variables. H was 0 here, H was 22, V was 0 here, V was unknown here, set A and B equal to each other and solved. Now, if V naught is 20.77 meters per second and theta is 16, then I get 20.77 times sine of 16 times divided by 2 times 9.8. I get that H is 1.67 meters. Does that make sense? He's essentially jumping off a 16-meter high, and he's only going 1.67 up in the air. And yeah, that does make sense because that ramp is really low. If he increased his weight by putting on a backpack, this is the type of question you would have on an exam from me. If I increase the mass of the skier, would it change his height? The height that he reaches? No. Why? Because you can see right here that his height does not depend on his mass. The reason why is that gravity is considered a constant force here, so mass comes out of it. Mass doesn't matter. This is also the reason why, I forget who it was, Galileo or whoever it was that dropped supposedly a cannonball and a feather and figured out they fell at the same rate. He really rolled small balls of different mass down inclines is how he really did that experiment, and he found that they in general had the same acceleration due to gravity. But anyway, yeah, this thing doesn't depend on mass at all, so his height would be exactly the same. That's one of those things that you have to know, and if you don't know it, you have to look at the equations. It tends to trick people, so they end up trying to rewrite it and change the mass, and then they realize, oh wait, no, it doesn't matter. So we have 3 more I want to do, and then I want to do a thing on potential energy graphs, and we'll be done. This one, you can see that these are starting to become energy problems with projectile motion. You can actually do projectile motion with energy. We could have done this part without, instead of, if you're launching at an angle of 16 degrees, the energy here is mv naught squared over 2, and the energy up here is mgh. So this is equal to mgh, right? No, don't want to do that. Hold on. Oh yeah, I do. Sorry. mgh plus what? What is the energy up here? So this is the part that generally throws people off, because you might go at the top here, oh, he's only got mgh at B and A. Let me actually back up for a second. I do want to totally explain this, because this is kind of funny. You guys are going to do an SLO at the end of the semester where you have to do that same projectile motion over again. So let me see if anyone can guess what's the problem here. So if I do A and I do B when it's at max height, and I write energy A, energy B, mv naught squared over 2, mvb squared over 2, mgha, mghb, and I say this is 0, and I say that h at A is 0, so that I can measure this, 0 to hb. What's wrong here? What's wrong here is it actually still has some mv squared at B. what it has is in the x direction. In the x direction, just because it's 0 on the y doesn't mean it's 0 on the x. So you could put that this is mvy squared over 2 plus mvx squared over 2 plus mgha. This is 0. These would cancel, and what you get is you get mvy squared over 2 is equal to mgha. And that cancels, and then you get what we got before, that HA is V sine theta over 2G. So just, if you try to do projectile motion, remember that the velocity is still in the X direction at the top of the max height, and you need to account for it. But thankfully, because the energy is independent in each direction, you can take the kinetic energy in the X and the kinetic energy in the Y and separate them out, which is kind of cool. All right, so here we're going to do the opposite one, where now it's going to shoot off from a spring, hit the ground. We know the target box is 2.16 meters away. Okay, and we know how far they compress the spring, and we know that V is going to launch only that way. Center of the marble falls short. So how far should they compress the spring to get a direct hit? Okay, so now what do we have to figure out here? What we have to figure out is what the energy is when it's originally compressed, when it leaves the gun, and when it hits the ground, okay? Now, in order to figure out how far away, how are we going to do that? Well, we're going to use the fact that X final minus X initial is equal to V naught of X times T, but V naught of X is actually VB here. So at A, energy at A, energy at B, energy at C. Energy at A is KXA squared over 2. We can write MVA squared over 2, but it's compressed. There's no energy there. Plus MGHA. This is why we write every term. Don't forget that this thing has some height. We're not sure what that height is, but we may need it. Energy at B, KXB squared over 2 plus MBB squared over 2 plus MGHB. And finally, the energy at C, MVC squared over 2 plus MGHC plus KXC squared over 2. Right away, we know this is no, this is no. It has no spring energy. But I still suggest you write it first, just so you don't forget terms that you may need. We're going to assume that HC is 0.
Sure.
Now, what we have is EA is equal to EB. And remember that we're trying to find VB. So EA is KXA squared, where XA is the amount that it would compressed. And EB is, I guess I should write this, although I don't really want to. MGHA and MGHB are the same. So if I set these equal, these go away for now. So I have MVB squared over 2. So I have that VB is equal to 2 over 2 K over M XA squared square rooted, or square root of K over M times XA squared. Now, I don't know K right now. But what I do know is I'm going to assume that X is 0. I don't know the time either. Yeah, I do. X final is equal to V naught, I'm going to call it VB times T. Y final minus Y initial is equal to V naught Y T minus GT squared over 2. It has no Y initial velocity at B. Therefore, and this is going to be h, whatever h is. Do I want to do that? I feel like there's a simpler way to do this. I may just want to find, oh, yeah, I'm done, sorry. I don't think I want to use that t. I don't want, so v final, no. Sorry, I'm trying to think how I want to do this. Oh, I know what I want to do. Okay, never mind, it's fine. The time that it's going to take to fall is going to be the same for both of them. How do I know that? Because the time only depends on y. So just trust me on that. So what we're going to do here is we've already found VB, and we found that x final. So x final is equal to VB over t, and x final 1, and then x final 2 is equal to VB. I'm going to call that 1 and 2 times t. T's are the same. Therefore, x final 1 is equal to VB1, and x final 2 is equal to VB2. I found that VB was k over m xa squared, square root. Let me put this back to a square though. So this squared, this squared, this squared, this squared. So x final 1 squared over x final 2 squared is equal to k over m xa squared over k over m xb squared. These are the same. So what I get is that x final 1 squared over x final 2 squared is equal to xa squared over xb squared, the amount I compressed it. What I'm trying to find is how far should I compress it for a direct hit? Well, I want xb. So xb squared is xa squared times x final 2 squared over x final 1 squared. That is, xa was, so target box D is, so x final 2 is 2.16. 2.16 meters. X final 1 fell short of that by 25.2 centimeters. So 2.16 minus 25.2. I'm sorry, 0.252. Is 1.908. And XA was 1.1 centimeters. They wanted in meters, so XA was 0.011. Okay, so I do all that, and what I get is I get 0.011 squared. 2.16 over to 1.908. This whole thing squared. So 2.16 divided by 1.908. And then I take the square root. I get 1.245. This ends up being 0. If you take the square root of both sides, 0.01245. So this is a little hard. This is kind of a hard problem. What we did was we solved for EA and EB. EA is equal to EB, and we got that KXA squared over 2 was equal to MBB squared over 2, And then we found that x final minus x initial was equal to BB times T. And then we used the fact that they did 2 trials, and we used that divided by x final minus x initial equal to BBT 1 and 2, 1 and 2. So this is trial 1, and this is trial 2. And we set those equal. These canceled. The times were the same because they only depended on y. So we got x final 1 and x final 2 is equal to v1 over vb. And then I needed to square these just to make it easier. This became vb squared was kxa squared over m. And therefore, this became xa1 squared over xa2 squared. And from there, you could solve for xa2 because you knew that x final 1 was the one that was short and x final 2 was the one that was in the middle. Not too bad. I mean, it's bad, but it's not completely unreasonable. All right, now we have to deal with friction. Actually, in the next 2, and those are the final 2 where we do some potential energy, we have friction. These are a little bit harder. So we're told there's a block that's accelerated from rest by a compressed spring. It leaves the spring's relaxed length. So at A, it's been compressed by, well, we don't know, and then travels over a frictional region where this distance is 8.2 meters and mu is 0.244. So what's the increase of thermal energy, the maximum kinetic energy, and the original compression distance? So we're actually going to work backwards, and I'll show you how. At EA, and this is A, when it's compressed, once it's fully past the relaxed point, and then at C where it stops. So EB and EC. As I said, just write down this, and we'll fill in everything else in a minute. MGHA, MGHB, MGHC, springs. Don't worry about friction yet. We're going to add friction in a minute. And that's where things get tricky. Okay, so at A, the spring compressed. But at B and C, it's not. It's not even in contact with the block anymore. So we can get rid of the spring at those. We can get rid of all the H's. They're the same, so they all just cancel each other. And finally, at C, it has no velocity. And at A, it has no velocity. So what we get is we get that EA is equal to EB is equal to EC, but there's friction between B and C. That means we have to add the work done by friction. And the work done by friction is mu n. N for a block on a surface is mg, right? So this is mg. This is mu mg. Now EA is equal to EB, and they're both equal to mu mg. The amount of energy here and the amount of energy here gets used up here as friction. Friction becomes heat, okay? So for answer number 1, the increase in thermal energy is equal to the energy of friction. We were given 0.244, we were given 3.4, and we were given, oh shoot, I'm sorry, you guys. I always forget the stupid D. Force times distance is work F dot D. I always remember the force and forget the distance. So that's D. We know all those, mu 0.244 times 3.4 kilograms times 9.8 times, how far did it travel? 8.2. And we get 66.7 joules. We're awesome. Now, that is the increase in thermal energy. but that's also the maximum kinetic energy that the block had. Because at B, all it had was kinetic energy. This was mvb squared over 2. And this was kxa squared over 2. And they're all equal to the same energy, because this energy became the energy in the compressed spring, became the kinetic energy at B, became thermal energy released as heat due to friction. And they were all 66.67 joules. So this maximum kinetic energy, same. Then they ask us for XA. How far was it initially? Why do you always do that to me? How far was it initially compressed? If kx squared over 2 is equal to 66.7 joules, and k was 640, then you get that x is equal to 2 times 66.7 joules divided by k, or 640. 2 times 66.7 divided by 640. Take the square root of this answer, and I get 0.4565. I don't know why they get 64, but maybe they didn't round that 66.7. So the main takeaways here are, when you have friction, you have to add it to the final energy after it passes through. So EA in this problem was equal to EB, but they were not equal to EC. What they were equal to was they were equal to EC plus the work done by friction from B to C, okay? Or another way to say this is that EC was equal to EB minus the work of friction from B to C, or EA minus the work of friction from B to C. That's because the friction took energy out of the system. So initially, it had EA, the amount of energy that was stored in the spring. At B, it still had that energy, but now that energy is kinetic energy. And at C, it has no energy because all that energy was lost to friction. I hope that makes sense to you guys. Friction's a little tough to deal with. It's a little bit of a pain. We'll do this one super fast. I know it's getting long, and then we'll talk about potential energy, and then we'll be done. So this one, I'm just going to kind of describe what we do. This block slides along this track and then comes up higher, and it goes through this friction region, and we're told mu, and we're told what h is, and we want to find how long it takes to stop. Let's just write down our variables here, because we know that the energy has to be mgh plus kx squared over 2. None of these have a spring. So at A, we have mv squared. Why are you saving? Don't save. You suck. I didn't want it to save. That's all right. So we have at A, we have mba squared over 2 plus mgha. But we're going to say that HA is 0. Once it gets to D, which I'm going to call B, it has mvb squared over 2 plus mghb plus the work done by friction, which is mu mgd. Now we want D. HB is certainly there. There is no velocity. This is EA. This is EB plus work of friction. So we set EA equal to EB plus work friction, which is MVA squared over 2 is equal to MGHB plus mu MGD. But that means that mu MGD is equal to MVA squared over 2, the initial kinetic energy, minus the change of gravity. As it goes up, gravity takes energy out. the friction takes energy out. All this original kinetic energy became some potential energy of gravity and some friction work. Did I write that like that? I'm sorry. This should have been MGHD, HB. MGHB. So we could easily find for D by just dividing through this by mu mg. And I'll let you guys do that on your own. It's not hard. But all you have to do is set the energy at each area equal to each other. When there's friction, make sure you put it with the final energy where it came out of. All right, so last thing I want to talk about, because it's gotten long, potential energy curves. So I'm going to come back into Canvas. For those of you here still here, I want to show you something kind of cool. And hopefully you all have your Wiley stuff. So there's these things called potential energy curves. And if you go into the Wiley course material and read your book on here, it's really nice. I don't know, to have the ebook because they have little simulations. But what I want to tell you is when you're doing a lot of lab work, usually trying to figure out how things work or what a certain molecule is doing or can do, you do something called a potential energy diagram. And on a potential energy diagram, you map the potential energy, not the kinetic energy, but the potential energy versus distance. And then what you do, usually it's R, these are all X's because they're one-dimensional. But then what you do is the mechanical energy is the kinetic energy plus the potential energy. So let's say that this is your potential energy diagram, and we're going to start at, let's say, point E5 with heading to the left with 5 joules of mechanical energy. Where does it end up over here? Well, mechanical energy is the kinetic energy plus the potential energy. So what that means is it's mv squared over 2 plus, let's say, mgh if it's gravity. And the total of this energy is always a constant. So let's say we know that it's 5 joules. If we're traveling left, it can go down, come up, go down, and get up to 5 joules of potential energy. And at that point, it has no kinetic energy. So at this point where it has no potential energy, it has 5 joules. I mean, at the point where it has no kinetic, it has 5 joules of potential. At the bottom here, where it has no potential energy, it has 5 joules of kinetic energy. So you can read these graphs by seeing what happens if it has a certain amount of energy. What if I started it here, though, with only 3 joules of potential energy? It can't even get back up. So let me actually show you that in this kind of cool thing that I wanted you to see. I believe this is the one. Nope. This is the one. So this little slider lets you basically give it the amount of kinetic energy, right? Because that's mv squared over 2. And this is its potential energy graph. And you see that if we start it with this amount of potential energy, or kinetic energy, it only is able to go back and forth. At these turning points, it has all potential energy. At the 0, at the bottom of the valley, it has all kinetic. So it's going back and forth and back and forth. But watch what happens if we give it a little bit more. Okay. So it comes up and then it just barely goes over and it's able to go down the other side. So these are called like potential energy wells, basically. And if it just doesn't have quite enough, it never gets out of that well. Or if you give it a little bit of energy, it gets out of that well, which is kind of a weird way to see potential energy. But something that the reason why I'm not going to ever test you on these, I might give you a homework problem on them, but I'm not going to test you on them, is they're really useful for central force problems, for restoring force problems, for forces that are minus kx. You see them a lot in nature. You see them a lot in biology. You see them a lot in astrophysics. You see them in quantum. An electron trying to escape an atom kind of gets bound in this potential well where it can only go so far away before it becomes trapped on the other side. So it's kind of like going back and forth. And knowing how to read these is really important for that reason. I wanted to show you a problem that I'm not going to go totally through because it's 4 o'clock. And I know we go till 4:50, but I don't take breaks, and I'm sure you guys are probably tired too. And you have a quiz to do that we would normally do and all that good stuff. So this problem right here is a potential energy graph. And they're saying that this thing starts at 0.26, it's a 0.26 kilogram particle, that it starts at the point UB with 12 joules of potential energy and 7 joules of kinetic energy. I know this is kind of hard to see. A is 9 joules potential, B is 12, C is 20, D is 24. So if we look at this, it has a total of, at B, at this point, X is B, it would have a total of 19 joules. That means the highest point it can get up to is 19 joules. So if it's heading this way to the right, and let's say it starts somewhere between C and B, it's going to travel down. C is 20 joules. So it starts like here, it's going to travel down, get over this hill, come up and stop at 19 joules of potential energy, 0 joules of kinetic, and then head back the other way. And so you can figure out what the speed is because at every point it has mv squared over 2 plus mgh, or ke plus u is equal to 19 joules. It's a little bit weird is if we want to find the turning point between these two, because we know this is 20 and this A is 9. Hold on. You want to find the X position where the kinetic energy is 19, I'm sorry, the potential energy is 19 joules. You can do that by finding the slope. Because the slope from here to here, let's say this is a point with X, then the change of U over the change of X gives you the slope, and it's equal to the change of, so U from here to here is equal to there to there. So I'll show you that really fast just for this one. Call this 1 and call this 2. So we can see that this starts at 1 and goes to our, it goes to our, I'm going to call this T for the turning point, or TP, minus 1. This is X final minus X initial, over 20 minus 19. And that's equal to 3 minus our turning point, over at 3 we're at UA, which is 9. So 9 minus 19. Oh, I'm sorry, this should be 20 minus final minus initial. Oh yeah, no, I was, yeah, 19 minus 20. Okay, so we just basically set the slope from here down and the slope from, actually, maybe I should go up. No, it doesn't matter. The slope down is fine. Slope down, they're both negative. In fact, I don't want to do that. I'll get a negative number. So to solve this for the turning point, this is -1, this is -10. I get TP minus 1 over -1 is equal to 3 minus TP over -10. Multiply that through, I get -10 TP plus 10. All I did was I multiplied by -10 on both sides. And I got rid of this, and this, and then I multiplied by a negative sign to get rid of this 1, which means this is positive and this is negative, is equal to 3 minus plus TP. Okay. Combining like terms, I get 11 TP is equal to 7. And I know you probably can't follow my math, that's all right. So TP is 7 divided by 11, should be 0.636, which means I did that wrong. Oh, they wanted the speed at A and B. What is the position of the turning point? What did I do wrong? Let me go back and do this. So the slope of this line is delta U. Oh, I think I flipped it, which is why. Delta U over delta X, which is 20 minus 19 over, nope, 19 minus 20. 19 minus 20 over the change of X, which is X turning point minus 1. No, that is. That's that slope, which is -1 over XTP minus 1. This slope goes from X final to, or X turning point to 3, and UA is 9. So this is, U is 9, here U is 19, this is 3. So I get change of that, final minus initial over final minus XTP. Setting those equal, well, that's equal to -10 over 3 minus XTP. Setting these two equal to each other, canceling a minus sign, 1 over XTP minus 1 is 10 over 3 minus XTP. Or I'm just going to call these X. 3 minus X is equal to 10X minus 10, or 13 is equal to 11X. So X is equal to 13 divided by 11. Which feels a little wrong as well. Nope, that's right. That's the answer to D. If you're wondering though, if you're not following me exactly, let me show you exactly how they did this, or how, what I was trying to do. I know it's confusing doing those slopes. If this thing will open, why does this either? So when you come through the book and you can look at all these examples, where they show you in the book how to read a potential energy curve with different energy levels and what will happen. Essentially on the curve, as long as it has greater than a total energy greater than 4, a total mechanical energy, it's going to get away if it's heading to the right. If it has a total mechanical energy greater than 6, it's going to get away if it's heading left. So like here where it has 5, if it was heading to the left, it would get stopped here when it ran out of kinetic energy and all the mechanical energy became potential energy. And then it would head back the other way. And if it was somewhere down here, it would get trapped in these valleys. But you can actually go to this example. Right here. I don't know why. Sample problem 8.04, they actually take you through reading this graph to find this turning point. But the main idea is that you can set the slopes of it equal to each other. And because of that, you can easily find the turning point, where you wouldn't be able to find it just knowing the slope on the one side. But anyway, yeah, I know that's kind of exhausting, a pain. So next time that we get together on Thursday, we're not going to have a quiz, but we are going to have a lecture. We're basically going to start chapter 9. And chapter 9 is all something called momentum. And for those of you that are still with me, I said this before, I kind of talked about it before, but we basically have lied to you. What Newton's laws actually say are not F equals ma. What they really say what they really say is forces are the time rate of change of mass times velocity. And that's because the acceleration is this, but you could also have a mass that changes. So imagine that you shake up a soda can and you open it on ice and you let the thing go flying off across the ice. That soda can is changing its mass. And that change of mass is actually what's causing the soda can to go flying away. So what we're going to actually look at is this quantity P. So P is m times v. Super simple, right? Even simpler is that momentum conserved, which means that anytime something happens, we have to conserve momentum if there's no external forces, which means that in general, we just find the momentum before and the momentum after something happened, something that we want to know about, some physical process, and we can find the velocity. Super fast and easy. However, we need to understand how kinetic energy is conserved along with momentum. And so we had to understand this energy. Basically, what we're going to be able to do is solve using momentum and figure out what the velocities are. And then we're going to use energy to figure out what happened in the problem. And I know that sounds kind of nebulous and kind of mysterious, but it really is just momentum that we need to worry about. Conservation of momentum and conservation of energy. And they're very simple to understand, but there's they have a lot of bones on them. They have a lot of stuff happening in the background, to where if you just write down the equations and don't understand what's happening, you won't get it. But one of the coolest things in the world is that when you understand momentum, you can do things like how far a baseball gets hit, or how to save your life in a collision in between two cars, or how a figure skater can do a really, really awesome flip in the air and seemingly hardly move. It's amazing. And in a really, 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 really truthful sense, momentum is the key to the universe. Momentum is conserved just like energy. It can never be created or destroyed. It's always there. It comes from somewhere. It goes somewhere. So when you change something from momentum, you give it momentum. And I mean, I guess that's not totally true because it can be lost due to friction. But in a vacuum with no external forces, anything that interacts, all they do is exchange their momentums. And that quantity is always conserved going back and forth. That's true for planets. That's true for you. That's true for electrons. It's pretty cool stuff. So anyway, that's next time. I'm going to stop recording now. If you have any questions, let me know. Otherwise, see you next time. Cool. Thanks, Alyssa. I hope so.
Thank you so much, Professor. Have a wonderful day.
Thanks, guys.